Good day, ladies and gentlemen. This is Johan Venter from the University of Pretoria in South Africa. I'm presenting my paper titled Optimization of 4-transistor pixel structure BiCMOS detectors using Y-parameter representation, together with Professor Sinha. This paper introduces a mathematical relation between AC performance of 4-transistor pixel structure detector, which can be used to develop optimized detectors pre-manufacturing. This was done using small signal analysis and Y-parameter representation, where the process-dependent, process-independent parameters can be easily inserted in the mathematical model. Two 4-transistor pixel structure configurations were used to show the validity of the proposed model. Simulation results are presented, where the aspect ratio of the MOSFETs, bias voltage, and temperatures are varied. Using this work, detector designers can select desired transfer resistance gain and then calculate the required process-dependent, process-independent parameters. So why is all this necessary? So let's see in the next slide. Specialized imaging application using different methods have been shown significant progress. And the several detectors have been described in literature, but details about the readout circuitry are lacking. Some readout circuitry details are available for specific reasons, whereas the generic mathematical model is lacking. So this paper presents a small signal modeling of 4-transistor structures using Y parameters. Also makes it possible to determine the performance of these detectors at different operating temperatures. So the detectors itself have been described in literature, the specific detecting element. But the readout circuitry is where we found this somewhat lacking. So this work focuses on one method to characterize detectors in these in BiCMOS for optimization of the readout circuitry. So these are the two configurations we used in this work. The first is the normal classic 4-transistor pixel structure, and then the second one is the modified structure where we inserted this short. So it will become evident what this short did in the actual behavior. Briefly, the pixel itself, its DPH, is a reverse bias diode, or one can use a diode-connected BJT or HPT, where the base and the emitter is connected, forming a PN junction as well, using BJTs. Then the output, nothing is connected to the output, because we assume that the output to the next stage is the next stage is has got a high resistance. In conduction mode, we have to get the detector in conduction mode. To enable this, or to get to this, the gate drain voltage must be smaller than the threshold voltage. For this, we had to get M1, M2, and M3 to adhere to this condition. So for that, we shorted the gate and the drains. Then, when we transformed this to small signal models and rearranged, we get to this circuit. So in the A loop, it's the two gate source capacitance of M1 and M2. Now, since it's an input current and an output voltage, this A loop is 0. The F loop, however, it will not be 0, and that's where the modeling occurred. We didn't include the diode or the pixel in this side, which it's a current that's generated due to photon flux that falls onto the pixel, which and for that reason, it's not included here. So then, for Y11F and Y21F, when we made V2 0 and V1 with several Thevenin and Norton transformations, came out to this simple circuit, which is a voltage source and a resistance. Doing the same for V1 equals 0 to calculate Y1 2F and Y2 2F, we found, got this circuit with this equation. Then by doing the classical method of development with Y parameters and substituting everything in, we found that Y11F is this nice equation where RO1 is M1's output resistance in brackets 1 plus GM1 VGS1 close brackets plus RO2, which is the output resistance for M2, 1 plus GM2 VGS2, which is again for M2. Then by simply multiplying it with a negative, we could get Y21F. And much the same method has been used to do Y22F to get to this equation where VGM VGS3 is all of this. So then the same happened for Y12F. When we combined all of this and we found that the final model for the normal configuration for Y parameters is this. AutoHPT is the output resistance of the pixel. Now, we use diode-connected BJTs, and when we can short the base in the emitter, the eventual small signal model is only an output resistance, hence it's included here. But the classic Y parameter derivation is the admittance of the input side or the source, which sits below the line. So the admittance is the inverse of the resistance, which is given here. For the modified configuration, we found that this is the model, which is again a very nice model to use. The nice thing of this model is RO1, the output resistance, can be related to something else again with which you desire, and GM again to something else. So in this way, this model is adaptable to be able to use for a variety of different scenarios. Simulations for the normal configuration. Apologies for having this in red. When I compiled the presentation, it came out fine, but when I did the narration on this, it didn't come out correctly. So it looks like a solid line. So just to avoid confusion, I used a red line here. Now, the transfer resistance gain as the current source current varies the photon generated current for varying aspect ratios of M4, where M1, M2, and M3 is equal to 2. We've found that by increasing the aspect ratio, the gain decreases, as one can see here, aspect ratio 2, 6, and 10. Then when M1, M2, M3, and M4 is equal to 2, and varying the supply voltage, we found that by increasing the supply voltage, the gain decreases. So a decrease in supply voltage will get an increased gain, but not indefinitely. It will, at a stage, result in the transistor being switched off, which then is not worth it to work with. For M1, M2, M3, and M4 equals 10, the aspect ratios and varying supply voltage, again, the same trend happened, but the overall gain comparing to when it was 2 also dropped. When M1, M2, M3, and M4 equals 2, and varying temperatures, we found that by decreasing the temperature, the gain increases. Here at the top is 77 Kelvin, which is used in very cold temperatures, sometimes space. For the modified configuration, the graphs look a little bit different. For M1, M2, M3 equals 2 and varying M4, we found that by increasing it, the gain drops, which is a similar trend with the normal configuration. However, as the illumination increases, we see that it becomes relatively stable. which is quite different from the normal configuration. When in the modified configuration, the aspect ratio of each one plays a huge role, and several different combinations can be used in this. So for this one, I increased M3 to 10, and comparing to when M3 was 2, it was found that the gain dropped significantly by over 60 kV over A, 60 kilovolt ampere. By varying the supply voltage when aspect ratios are very low, at low illumination, it differs quite somewhat. But as the illumination increases, the gain stays relatively constant. When we increase M4, M3, M2, and M1 to 10 and vary the supply voltage, we get this different curve. So at low illumination, it stretches out even less, but and then at the higher illumination, it's becoming more stable. The most important thing is when this, due to the short in a modified configuration, we found that the temperature variation does not play a huge role. This makes this configuration for colder temperatures than room temperatures relatively stable with the output. This is just a summary of the discussion of the results. More or less covered this in the whole presentation. So just a couple of things of interest. The gain reduces as the aspect ratios of M1 to M4 is increased for modified pixel structure. The transfer resistant gains decreases as temperature is increased for the normal configuration. However, quite different from the normal one is when it stays, the transfer resistant gain stays constant as temperatures increase for the modified configuration. Even with a non-zero source body voltage, the simulation showed that it still stays constant, which is quite unique. In conclusion, this work, the small signal model, the small signal performance of 4 transistor pixels is shown using a Y-parameter modeling. Most important observations: transfer resistant gain mostly decreases as illumination increases. Detailed results showing the transfer resistant gains versus photon generated current when the aspect ratio, supply voltage, and temperature are varied. This is the process independent parameters. These models can be used to predict the performance of the 2 4 transistor pixel structure detectors, allowing for reduced design time and enabling the designer to develop optimized detectors pre-manufacturing. This is just a list of the references I used, which is also the references in the actual paper. And I thank you and invite any questions to be sent to my email address. And thank you very much. It was a pleasure presenting.